In the vast darkness of space, where silence reigns supreme and time moves to rhythms beyond human comprehension, there exists a phenomenon so beautiful, so fundamental to existence itself, that without it, we would not be here to wonder at its majesty. This is the story of stars, those brilliant beacons scattered across the cosmic ocean like luminous islands in an infinite sea. Tonight, we embark on a peaceful voyage through the life cycle of stars, from their gentle birth in clouds of gas and dust to their spectacular transformations in death. This is not a journey of urgency or alarm, but one of quiet contemplation, where we float through the mechanisms of stellar evolution as softly as starlight itself travels across the emptiness between worlds. The universe is approximately 13.8 billion years old, a time span so immense that our human lives are but the briefest flicker in comparison. Throughout this incomprehensible duration, stars have been born, lived their luminous lives, and died in ways both gentle and magnificent. They are the universe's great alchemists, forging within their cores the very elements that compose our bodies, our world, and everything we know. As you settle into this journey, imagine yourself drifting peacefully through space, untethered from earthly concerns, watching with patient eyes as cosmic processes unfold. There is no rush here, no deadline to meet. The stars have waited billions of years to share their stories, and they will wait billions more. We simply float, observe, and wonder at the serene beauty of stellar transformation. The light from distant stars has traveled for thousands, millions, sometimes billions of years to reach our eyes. When we gaze upward on a clear night, we are not seeing the universe as it is now, but as it was looking backward through time itself. The star Betelgeuse, that reddish jewel in the constellation Orion, shows us light that left its surface approximately 650 years ago. If it were to explode tonight, we would not know for centuries to come. This gentle disconnection from immediate time, this patient unfolding of cosmic events, sets the perfect tone for our exploration. In the chapters ahead, we will move slowly through the stellar life cycle, pausing to appreciate each phase, each transformation, each quiet miracle of physics and chemistry that makes the universe luminous. From the cold, dark molecular clouds where stars first stirred to life, to the glowing planetary nebulae and dense white dwarfs that mark their final chapters, we will witness the complete story. Along the way, we will encounter real phenomena observed by astronomers, real stars cataloged and studied, real processes confirmed by decades of careful scientific observation. So breathe deeply, relax your shoulders, and let your mind drift upward into the cosmic ocean. The stars are waiting to share their ancient secrets, and we have all the time in the universe to listen. Deep within our Milky Way galaxy, in regions so dark that they appear as voids against the starry background, vast clouds of molecular hydrogen drift in the silence of space. These are the stellar nurseries, the birthplaces of stars, and they're among the most serene and beautiful structures in the cosmos. The most famous of these is the Orion Molecular Cloud Complex, located approximately 1,500 light-years from Earth, a structure so massive that it contains enough material to create thousands of stars like our Sun. These molecular clouds are cold, extraordinarily so. Their temperatures hover around minus 260 degrees Celsius, just a few degrees above absolute zero, the coldest temperature possible in our universe. At these frigid temperatures, hydrogen molecules move sluggishly, their atomic dances slowed to a gentle drift. The clouds are composed primarily of hydrogen, the universe's most abundant element, along with helium and trace amounts of heavier elements. Carbon, oxygen, nitrogen, and dust grains so small they can only be seen under the most powerful microscopes. Within these clouds, the density of matter is incredibly low by terrestrial standards. In many regions, each cubic centimeter contains only a few hundred to a few thousand molecules. For comparison, the air you breathe contains approximately 10 quintillion molecules in the same volume. Yet despite this incredible thinness, the sheer size of these clouds, often spanning hundreds of light years across, means they contain tremendous mass, sometimes hundreds of thousands of times the mass of our Sun. The Eagle Nebula, cataloged as Messier 16 and located about 7,000 light-years away in the constellation Serpens, contains one of the most photographed stellar nurseries in existence. Within it are the famous pillars of creation, towering columns of gas and dust photographed by the Hubble Space Telescope in 1995 and again in enhanced detail in 2014. These pillars stretch for approximately 4 to 5 light-years, each one taller than the distance from our Sun to the nearest star, Proxima Centauri. The process of star formation begins with a subtle disturbance in these peaceful clouds. Perhaps a nearby supernova sends a shock wave rippling through the gas, or the gravitational influence of a passing star cluster creates compression in certain regions. Maybe the cloud itself, having grown massive enough, begins to collapse under its own gravity. Whatever the trigger, small pockets within the cloud begin to contract. As these regions contract, they grow denser. Gravity, that patient and inexorable force, pulls more material inward. The process is extraordinarily slow by human standards. These early contractions might take hundreds of thousands of years to show significant change. But in cosmic time, this is merely a moment, a quick breath in the long life of the galaxy. The Taurus molecular cloud, located about 430 light-years from Earth, is currently in the process of forming stars. Astronomers have identified hundreds of young stellar objects within it, stars at various stages of their early development. Some are still deeply embedded in their natal cocoons of gas and dust, completely invisible to optical telescopes, but glowing brightly in infrared wavelengths as they warm their surroundings. As a contracting region grows denser, it begins to fragment into smaller clumps. Each clump becomes a potential star. The center of each clump, now called a protostellar core, grows warmer as gravitational potential energy converts to heat. This is not the heat of fusion, not yet, but the gentle warmth of compression, the same principle that makes a bicycle pump grow warm as you pressurize air within it. Over hundreds of thousands of years, these cores continue to collapse. Material from the surrounding cloud falls inward, spiraling into a disk around the growing protostar. This disk, called an accretion disk, is critically important. From its material, planets may eventually form, though that is a story for another time. For now, the disk feeds the growing star, adding mass to its central core. The youngest protostars, classified as Class 0 objects by astronomers, are still more enveloped than star. More than half their mass remains in the surrounding infalling material. These objects emit most of their energy in the far infrared and submillimeter wavelengths, invisible to our eyes, but detectable by specialized telescopes like the Atacama Large Millimeter Array in Chile or the James Webb Space Telescope. As the protostar continues to grow, it enters what astronomers call the T Tauri phase, named after the star T Tauri in the constellation Taurus, the first of its type to be identified. T Tauri stars are young, typically less than 10 million years old, and still surrounded by their accretion disks. They are variable stars, their brightness fluctuating over days or weeks as material from the disk falls onto their surfaces. Our own sun almost certainly passed through a T Tauri phase approximately 4.6 billion years ago. These young stars often produce powerful stellar winds and jets, streams of material that shoot outward along their rotational axes at speeds of hundreds of kilometers per second. The Herbig-Haro objects, such as HH212 located about 1,300 light-years away, are spectacular examples of these jets. They create glowing shock waves when they collide with surrounding gas, painting beautiful symmetric patterns in space. Throughout this entire process, from the first subtle collapse of a molecular cloud region to the formation of a T-Tauri star, millions of years have passed. Yet for the cloud itself, for the galaxy, this is hardly any time at all. Stars are being born continuously throughout the Milky Way at a rate of approximately 1 to 3 new stars per year. Some are tiny red dwarfs with masses barely a tenth that of our Sun. Others are massive blue giants with dozens of times the Sun's mass, burning brilliantly but briefly. The Carina Nebula, located about 7,500 light-years away, is one of the largest stellar nurseries visible from Earth. Within it, the Hubble Space Telescope has identified numerous stellar nurseries, including the spectacular Mystic Mountain, a 3-light-year-tall pillar of gas and dust sculpted by ultraviolet radiation from nearby massive stars. At its peak, infant stars are forming, each one surrounded by its disk of material, each one beginning the long journey toward stability. As we drift away from these stellar nurseries, leaving behind the cold, dark clouds and the warm glow of protostars, we prepare for the next chapter in the stellar story. The stars are gathering their strength, their cores growing hotter and denser with each passing millennium. Soon, in cosmic terms, they will ignite the fusion fires that will sustain them for billions of years. But for now, they rest in their cradles, growing, warming, and preparing for the long, luminous lives ahead. Deep within the contracting core of a protostar, something extraordinary is about to happen. For millions of years, the young star has been warming itself through gravitational contraction alone, growing denser and hotter as material continues to fall inward. The temperature at its center has climbed steadily, 10,000 degrees, 100,000, now approaching 10 million degrees Celsius. The pressure is immense, with matter compressed to densities hundreds of times greater than the densest materials on Earth. At these extreme conditions, the hydrogen nuclei at the star's core are moving at tremendous speeds, their thermal energy having overcome the usual sluggishness of cold matter. They collide with each other constantly, millions upon millions of collisions every second. Most of these collisions result in nothing. The positively charged nuclei simply bounce off one another, repelled by electromagnetic force. But occasionally, very rarely, two hydrogen nuclei collide with such energy that they overcome their mutual repulsion and fuse together. This is the moment of ignition, the birth of true starlight. The fusion of hydrogen into helium, the same process that has powered our sun for 4.6 billion years and will continue to power it for another 5 billion more. This reaction, called the proton-proton chain in stars like our sun, converts mass directly into energy according to Einstein's famous equation, E equals mc squared. Even though only a tiny fraction of the hydrogen's mass is converted, about 0.7%, the energy released is staggering. In our sun, approximately 600 million tons of hydrogen are fused into helium every second. This process releases energy equivalent to billions of nuclear weapons detonating simultaneously. Yet this tremendous power is generated in the sun's core, a region only about a quarter of the sun's radius, where temperatures reach 15 million degrees Celsius and the density is approximately 150 times that of water. The energy released by fusion does not immediately escape the star. Instead, it begins a long, slow journey outward through the stellar interior. In the core and the radiative zone surrounding it, energy travels in the form of photons, packets of light, but these photons cannot move freely. They are constantly absorbed and re-emitted by the dense plasma, taking a random walk through the stellar material. This journey from the core to the surface takes an extraordinarily long time. Scientists estimate that a photon generated in our sun's core will take between 100,000 and 170,000 years to reach the surface, traveling a straight-line distance of only 700,000 kilometers, but taking a zigzagging path so convoluted it covers millions of light-years worth of total distance. Once it reaches the surface, that same photon takes only about 8 minutes to cross the 150 million kilometers to Earth. When fusion begins in a protostar's core, something remarkable happens. The collapse stops. For millions of years, gravity has been pulling the star inward, compressing it ever smaller. But now, the outward pressure from fusion-generated heat exactly balances gravity's inward pull. The star reaches what astronomers call hydrostatic equilibrium, a perfect, stable balance that will last for billions of years. This is the defining moment when a protostar becomes a main sequence star. Main sequence stars are in the prime of their lives, steadily fusing hydrogen into helium in their cores. Our Sun is a main sequence star, as are approximately 90% of all visible stars in the night sky. They range from the cool, dim red dwarfs like Proxima Centauri, with surface temperatures around 3,000 degrees Celsius and luminosities less than 1% that of our Sun, to the hot, brilliant blue stars like Rigel and Orion, with surface temperatures exceeding 11,000 degrees Celsius and luminosities tens of thousands of times greater than our Sun. The mass of a star determines almost everything about its life. Low-mass stars, those with less than half the mass of our Sun, will burn their hydrogen fuel very slowly and efficiently. Proxima Centauri, our nearest stellar neighbor at just 4.24 light-years away, has a mass only about 12% that of the Sun. It will continue fusing hydrogen for trillions of years, far longer than the current age of the universe. Medium-mass stars like our Sun find a middle path. The Sun has been on the main sequence for about 4.6 billion years and will remain there for approximately another 5 billion years before exhausting the hydrogen in its core. During this time, it has been remarkably stable, varying in brightness by less than 1% over centuries. This stability has been crucial for the development and persistence of life on Earth. High-mass stars, those with more than 8 times the Sun's mass, live fast and die young. Despite having much more fuel than lower-mass stars, they burn through it at prodigious rates. A star like Rigel, with approximately 21 times the Sun's mass, will exhaust its core hydrogen in only about 8 million years, less than 1,000th the lifespan of our Sun. These massive stars burn so intensely that they shine with the light of tens of thousands of suns, making them visible across vast cosmic distances. The color of a star tells us about its surface temperature. Red stars like Betelgeuse are relatively cool, with surface temperatures around 3,500 degrees Celsius. Yellow stars like our Sun are hotter at about 5,500 degrees Celsius. White stars are hotter still, and blue stars like Rigel are the hottest of all, their surfaces blazing at temperatures exceeding 10,000 degrees Celsius. This relationship between temperature and color was first systematically organized in the early 20th century by astronomers Annie Jumpcannon and her colleagues at Harvard College Observatory. They developed the stellar classification system still used today: O, B, A, F, G, K, M, from hottest to coolest. Our Sun is a G-type star. The coolest main sequence stars are M-type red dwarfs, while the hottest are O-type blue giants. As a newly ignited star settles onto the main sequence, it has achieved a state of grace, a long, stable period of steady hydrogen fusion. It will change little during this time. The Sun's luminosity has increased by about 30% since it first ignited, a gradual brightening over billions of years, but this change is imperceptible on human timescales. Around these newly formed stars, the remnants of their accretion disks may be coalescing into planets. Our own solar system formed from such a disk, with the rocky inner planets condensing from heavier elements close to the Sun and the gas giants forming in the cooler outer regions. The Atacama Large Millimeter Array has photographed many of these protoplanetary disks around young stars, revealing gaps and rings where planets are likely forming right now. One particularly stunning example is HL Tauri, a young star about 450 light-years away in the constellation Taurus. ALMA images from 2014 showed its protoplanetary disk in unprecedented detail, revealing multiple concentric gaps carved by forming planets. The system is only about 1 million years old. For comparison, Earth is 4.5 billion years old, yet already several planet-sized bodies have cleared distinct paths through the disk. The transition from protostar to main sequence star is not instantaneous, but neither is it violent. There is no explosion, no sudden flash. Instead, there is a gentle settling, a gradual stabilization as the star finds its equilibrium. The stellar winds that characterized its youth begin to diminish. The surrounding nebulosity, lit by the star's radiation, glows with the soft colors of ionized gas: red from hydrogen, green from oxygen, blue from ionized helium. As we observe these newly born stars, scattered across stellar nurseries like the Orion Nebula, we are witnessing the universe continually renewing itself. Each star is a new beginning, a fresh supply of energy that will shine for millions, billions, even trillions of years. In their light, planets may form, atmospheres may develop, and perhaps, on some distant world circling a star we cannot yet name, life itself may be stirring. For now, these young stars simply shine, quietly converting hydrogen to helium in their cores, adding their light to the cosmic ocean, beginning the long, luminous journey that defines a star's existence. Imagine a state of perfect balance, where every force finds its counterpart. Every push meets an equal pull, and stability reigns for billions of years. This is the main sequence phase of a star's life, a long, peaceful era of steady hydrogen fusion that represents the vast majority of a star's lifetime. It is here, in this extended period of equilibrium, that stars truly shine in their full glory, reliable and constant across the cosmic ocean. Our sun, that familiar yellow orb that rises each morning and sets each evening, is approximately halfway through its main sequence lifetime. For 4.6 billion years, it has maintained an almost perfect balance between the crushing force of gravity pulling inward and the tremendous pressure of fusion pushing outward. This balance is so precise that the sun's radius varies by less than a few kilometers, an imperceptible fraction of its 1.4 million kilometer diameter. At the heart of this equilibrium lies the fusion process. In the sun's core, where temperatures reach 15 million degrees Celsius, hydrogen nuclei are constantly fusing into helium through the proton-proton chain reaction. This process occurs in several steps. First, two protons fuse to form a deuterium nucleus, heavy hydrogen, releasing a positron and a neutrino. The deuterium then captures another proton to form helium-3, releasing a gamma ray. Finally, two helium-3 nuclei collide to form helium-4, releasing two protons back into the mix. This elegant dance converts about 600 million tons of hydrogen into approximately 596 million tons of helium every second. The missing 4 million tons? That mass is converted directly into energy, radiating outward to eventually warm our planet and illuminate our skies. Despite this seemingly enormous rate of consumption, the sun contains enough hydrogen to continue this process for another 5 billion years. The energy generated in the core must travel through several distinct layers before reaching the surface. In the radiative zone, extending from the core to about 70% of the sun's radius, energy moves outward primarily through radiation, photons being absorbed and re-emitted countless times, gradually working their way toward the surface in that 100,000-year journey we mentioned earlier. Beyond the radiative zone lies the convective zone, where the plasma becomes cool enough and opaque enough that radiation alone cannot efficiently transport heat. Here, convection takes over. Hot plasma rises toward the surface, cools, and sinks back down in enormous circulating cells. These convection cells are visible on the sun's surface as granulation, a constantly changing pattern of bright centers, rising hot plasma, and darker edges, sinking cooler plasma. Each granule on the sun's surface is typically about 1,000 kilometers across, roughly the distance from New York to Florida, and lasts for only about 8 to 20 minutes before being replaced by new rising plasma. When observed through specialized solar telescopes, the sun's surface appears to boil with these granules, a dynamic display of convection in action. The visible surface of the sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. This is the layer we see when we look at the sun, always with appropriate eye protection. It's here that the photons, after their epic journey from the core, finally escape into space, free to travel in straight lines at last. 8 minutes later, some of them reach Earth, carrying the energy that drives our weather, our climate, and ultimately, all life on our planet. Different stars experience their main sequence phase in dramatically different ways. Red dwarf stars, the most common stars in our galaxy, burn their hydrogen fuel with remarkable efficiency. Proxima Centauri, at just 4.24 light-years away and visible only through telescopes, has a mass about 12% that of the Sun. Its low mass means lower core temperatures and pressures, resulting in a much slower fusion rate. But this seeming disadvantage is actually Proxima Centauri's secret to longevity. While it shines with less than 1% of the Sun's luminosity, it will continue fusing hydrogen for an estimated 4 trillion years, about 300 times the current age of the universe. Moreover, red dwarfs are fully convective, meaning their entire mass is constantly mixed. Unlike the Sun, which only fuses hydrogen in its core, red dwarfs will eventually fuse nearly all of their hydrogen, using their fuel with remarkable efficiency. At the other extreme are the massive blue stars, the giants of the stellar population. Consider Rigel, the brilliant blue-white star that marks the foot of Orion the Hunter. With a mass approximately 21 times that of the Sun, Rigel's core reaches much higher temperatures and pressures. Its fusion rate is correspondingly intense, making it shine with the luminosity of about 120,000 suns. But this brilliance comes at a cost. Rigel will exhaust its core hydrogen in only about 8 million years total. Having already spent most of that time, Rigel is actually nearing the end of its main sequence phase. When it leaves the main sequence, its evolution will be rapid and dramatic. But that is a story for upcoming chapters. The Hertzsprung-Russell diagram, developed independently by Ejner Hertzsprung and Henry Norris Russell in the early 20th century, plots stars by their luminosity versus their temperature. When astronomers plot thousands of stars on this diagram, a clear diagonal band emerges, the main sequence, running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right. About 90% of all stars fall somewhere along this band. Our sun sits comfortably in the middle of the main sequence, neither particularly hot nor cool, bright nor dim. It's classified as a G2V star. G2 indicates its temperature class, and V, the Roman numeral 5, indicates it's a main sequence star. This middling nature has been fortunate for Earth. More massive stars might have exhausted their hydrogen before complex life could evolve, while orbiting too close to a red dwarf might expose a planet to intense stellar flares. The Sun's mass also determines its evolution. Stars convert hydrogen to helium in their cores, but only the core is hot enough for fusion. As helium accumulates in the center, the core slowly grows denser and hotter. The Sun is about 30% brighter today than when it first reached the main sequence 4.6 billion years ago, a gradual increase caused by this changing core composition. This brightening, called the faint young sun paradox, presents an interesting puzzle for Earth's climate history. The early Earth received about 70% of the solar energy it receives today. Yet, geological evidence shows liquid water existed on Earth's surface as far back as 4.4 billion years ago. The resolution likely involves higher concentrations of greenhouse gases in Earth's early atmosphere, compensating for the dimmer young sun. Throughout the galaxy, hundreds of billions of main sequence stars are quietly going about their business of fusing hydrogen into helium. In the Pleiades star cluster, also known as the Seven Sisters, about 440 light-years away, we can see main sequence stars of various ages. The brightest members, massive blue stars, are only about 100 million years old, young by stellar standards. They form together from the same molecular cloud and are gradually drifting apart as the cluster ages. In the ancient globular cluster M13, located about 25,000 light-years away in the constellation Hercules, we find a very different population. This cluster is approximately 11.65 billion years old, nearly as old as the universe itself. Its most massive stars exhausted their hydrogen billions of years ago and have long since evolved into later stages. What remains on the main sequence are primarily low-mass stars, patiently burning their hydrogen, some of which will continue to shine for trillions of years to come. The main sequence phase is fundamentally a period of stability, but it is not entirely without variation. Most main sequence stars show some degree of stellar activity, magnetic phenomena that can create star spots, flares, and coronal mass ejections. Our Sun goes through an 11-year activity cycle, during which the number of sunspots waxes and wanes. At solar maximum, dozens of sunspot groups might hit the solar surface. At solar minimum, days or weeks might pass with no spots at all. Some young stars show far more dramatic activity. UV Ceti, a red dwarf star about 8.7 light-years away, is known for powerful flares that can briefly increase its brightness by up to 10 times. These flares release enormous amounts of energy, though still tiny compared to the star's total output. For any planets orbiting close to such stars, these flares could present challenges for the development or persistence of life. As we drift peacefully through our survey of main sequence stars, we observe the universe's engines of light steadily at work. From the tiniest red dwarfs, barely warm enough to fuse hydrogen, to the magnificent blue giants, burning with the fire of thousands of suns, each star maintains its own perfect balance. They are the universe's great sustainers, converting mass into energy, warming planetary systems, and giving the cosmos its luminous beauty. Deep within a main sequence star, invisible to any telescope yet fundamentally important to the star's fate, a subtle transformation is occurring. At the very center of the core, where temperatures are highest and fusion most vigorous, hydrogen is being consumed and helium is accumulating. This helium, the ash of hydrogen fusion, cannot yet fuse at these temperatures and pressures. It simply accumulates, growing denser and more massive as eons pass. In our Sun, this process has been ongoing for 4.6 billion years. Approximately 37% of the hydrogen in the core has been converted to helium. The core now contains a mixture of both elements, with the helium fraction slowly but inexorably increasing. This gradual change in composition has profound implications for the star's future, though its effects unfold over timescales so long that countless human civilizations could rise and fall without noticing any difference in the Sun's appearance. The accumulation of helium in the core affects the star in several subtle ways. Helium atoms are heavier than hydrogen atoms and pack together more efficiently. So, as the helium fraction increases, the core becomes slightly denser. This increased density strengthens gravity's pull, which in turn slightly increases the core temperature. The higher temperature accelerates the fusion rate, causing the star to slowly brighten over time. This is why the Sun today is about 30% more luminous than when it first joined the main sequence. This brightening continues at a rate of about 1% every 110 million years. Imperceptible on human timescales, but significant over geological time. In another billion years, the Sun will be about 10% brighter than today, potentially making Earth uncomfortably warm for life as we know it. For most of a star's main sequence lifetime, this helium accumulation proceeds without crisis. The star remains stable, the fusion continues, and the helium core grows gradually. But eventually, all the hydrogen in the core will be exhausted. What happens then depends critically on the star's mass. In low-mass stars like our Sun, this moment marks the end of the main sequence phase. When the core hydrogen is finally depleted, fusion in the core ceases. Without the outward pressure from fusion, gravity begins to compress the core once more. As the helium core contracts, it heats up, but initially it does not get hot enough to fuse helium. Instead, something interesting happens in a shell surrounding the inert helium core. This shell still contains hydrogen, and as it heats up from the contracting core beneath it, it begins to fuse. Shell hydrogen burning, as astronomers call it, actually produces more energy than the core fusion did during the main sequence phase. This extra energy causes the star's outer layers to expand dramatically. The star begins its transformation into a red giant, but we will explore that journey in the next chapter. In massive stars, those with more than 8 times the Sun's mass, the story unfolds differently. When these stars exhaust their core hydrogen, their tremendous mass creates much higher core pressures during contraction. These higher pressures and temperatures allow the core to heat up enough to ignite helium fusion long before the outer layers expand significantly. Helium fusion occurs through a process called the triple alpha process. 3 helium, 4 nuclei, also called alpha particles, hence the name, combine to form a single carbon, 12 nucleus. This process requires temperatures of at least 100 million degrees Celsius, about 7 times hotter than is needed for hydrogen fusion. The energy release per fusion event is less than in hydrogen fusion, but the higher temperatures mean the reaction proceeds rapidly once initiated. Consider the star Betelgeuse, the red supergiant that marks Orion's shoulder. With a mass approximately 16 to 19 times that of the Sun, Betelgeuse exhausted its core hydrogen millions of years ago. Its core has since fused helium into carbon and oxygen and has continued to even more advanced fusion stages, creating elements like neon, magnesium, and silicon. The star's outer layers have expanded to a diameter approximately 700 times that of the Sun, large enough that if it replaced our Sun, it would extend beyond the orbit of Mars. The transition from hydrogen to helium fusion represents a critical threshold in stellar evolution. For low-mass stars, it marks the beginning of the end. They will never achieve temperatures high enough to fuse elements heavier than helium. For massive stars, it's merely the first step in a cascade of fusion processes that will create increasingly heavy elements in their cores. Intermediate mass stars, those between about 2 and 8 solar masses, follow a path between these extremes. After exhausting their core hydrogen, they too develop helium cores surrounded by hydrogen-burning shells. They expand into red giants, but their greater mass allows them to eventually ignite helium fusion in their cores, becoming stable once more for a time. The star Arcturus, a brilliant orange-red star about 37 light-years away in the constellation Boötes, is likely in the helium fusion phase of its evolution. With a mass slightly greater than the Sun's, Arcturus has already expanded to about 26 times the Sun's diameter. Its core is now fusing helium into carbon and oxygen, though this phase will be much shorter than its time on the main sequence. Perhaps only 100 million years compared to billions of years of hydrogen fusion. The structure of an evolved star becomes increasingly complex as fusion proceeds. In the most massive stars, the core develops a layered structure reminiscent of an onion. At the center lies iron, the end product of fusion, which we'll explore later. Surrounding this are shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen, each shell fusing its respective element into the next heavier one. This layered structure has been confirmed through detailed computer models of stellar evolution. These models, refined over decades, can predict with remarkable accuracy how stars of different masses will evolve, when they will transition between fusion stages, and ultimately how they will die. Observations of stars at various evolutionary stages have consistently validated these models. The timescales for helium core growth vary enormously with stellar mass. In our Sun, the helium core has grown over 4.6 billion years and will continue to grow for another 5 billion years or so before core hydrogen is exhausted. In a red dwarf like Proxima Centauri, the helium core will grow for trillions of years. In a massive star like Rigel, the process takes only millions of years. These different timescales mean that stars born at different times in the galaxy's history have reached very different evolutionary stages. The most massive stars from the early universe have long since died, while the smallest red dwarfs born in that same era are still peacefully fusing hydrogen in their cores, appearing almost identical to red dwarfs born just yesterday in cosmic terms. The Eagle Nebula's pillars of creation, those towering columns of gas and dust, contain embedded stars at various stages of core evolution. Some are still protostars, not yet fusing hydrogen. Others are newly arrived on the main sequence, their helium cores just beginning to form. A few massive stars nearby have already evolved past the main sequence entirely, their ultraviolet radiation sculpting the very pillars from which they were born. As the helium core grows within a star, it is like a clock ticking down to transformation. For billions of years, the change might seem negligible, almost imperceptible, but the inexorable laws of physics are at work, and eventually, every hydrogen-fusing star must face the exhaustion of its core fuel. When that moment comes, the star's long period of stability will end, and a new chapter of its existence will begin. For now, across the galaxy, within billions of main sequence stars, helium cores are growing. Helium atoms settle into the centers of stars, compressed by the weight of the material above, waiting patiently for the temperatures and pressures that might, or might not, eventually ignite them into fusion. The universe continues its patient work of transformation, building helium cores atom by atom, second by second, across cosmic time. When a star like our Sun exhausts the hydrogen in its core, a remarkable transformation begins. The inert helium core, no longer supported by fusion pressure, contracts under gravity's relentless pull. This contraction heats the core and, more importantly, heats the shell of hydrogen surrounding it. When this shell reaches fusion temperatures, something paradoxical happens. The star begins to expand. This seems counterintuitive at first. The core is contracting, yet the star as a whole is growing. But the physics is clear. The shell fusion produces more energy than core fusion did, and this extra energy pushes the star's outer layers outward. Over millions of years, a star like the Sun will expand to perhaps 200 times its current diameter, becoming a red giant. Arcturus, that bright orange star visible in spring and summer skies, shows us what our Sun will become. Located about 37 light-years away in the constellation Boötes, Arcturus has expanded to roughly 26 times the Sun's diameter. Its surface temperature has dropped to about 4,300 degrees Celsius, cooler than the sun's 5,500 degrees, giving it that characteristic orange-red hue. Yet despite its cooler surface, Arcturus shines with about 170 times the sun's luminosity, simply because its surface area is so much larger. The journey from main sequence star to red giant is not instantaneous. For a star like the Sun, the transition takes about 1 billion years. At first, the changes are subtle, a slight increase in size, a gradual brightening. But as the helium core continues to contract and the hydrogen shell fusion accelerates, the expansion quickens. When the Sun becomes a red giant in about 5 billion years, its outer layers will expand past Mercury's current orbit. Mercury itself will likely be consumed, spiraling into the Sun's expanding envelope through tidal interactions. Venus may share the same fate. Earth, while possibly surviving the expansion itself, will be scorched by the Sun's increased luminosity long before this final crisis. The oceans will boil away, the atmosphere will be stripped, and our planet will become a lifeless, desiccated rock. But let us not dwell on that distant catastrophe. Instead, let us appreciate the beauty of red giants as they exist throughout the cosmos. Aldebaran, the orange eye of Taurus the Bull, is another nearby red giant, about 65 light-years away. It has expanded to about 44 times the Sun's diameter and shines with approximately 425 times the Sun's luminosity. Its cooler surface temperature of about 3,900 degrees Celsius gives it that deep orange color that has fascinated observers for millennia. The structure of a red giant is fascinating. The core, made of inert helium, continues to contract. In stars like the Sun, this core cannot yet reach the 100 million degree temperature needed to fuse helium. There simply isn't enough mass to generate sufficient pressure. Instead, the core becomes increasingly degenerate, a state of matter where quantum mechanical effects become important. In degenerate matter, electrons cannot be compressed beyond a certain density due to the Pauli exclusion principle, a fundamental rule of quantum mechanics that prevents two electrons from occupying the same quantum state. This electron degeneracy pressure supports the core against further collapse, at least for a time. The core becomes incredibly dense. A teaspoon of this material would weigh several tons on Earth. Above this degenerate core, the hydrogen-burning shell continues its work, fusing hydrogen into helium and adding to the inert core's mass. Outside this, the star's envelope extends for millions of kilometers, forming a tenuous atmosphere. The outer layers of a red giant are so diffuse that they are closer to a laboratory vacuum than to any gas we encounter on Earth. Yet they contain most of the star's total radius. Convection plays a major role in red giants. Unlike the Sun, where convection occurs only in the outer 30% or so, red giants can have convection zones extending from just above the hydrogen-burning shell all the way to the surface. This deep convection brings material from deep within the star up to the surface, a process called dredge-up. Dredge-up has important consequences. It brings carbon-12 and other fusion products from the hydrogen-burning shell to the surface, enriching the star's atmosphere with these heavier elements. Spectroscopic observations of red giants show these enrichments clearly, confirming our models of stellar structure and evolution. Some red giants become variable stars, changing in brightness over regular periods. Mira, a red giant in the constellation Cetus about 300 light-years away, varies in brightness by a factor of about 250 over a period of approximately 332 days. At its brightest, Mira is easily visible to the naked eye. At its faintest, it requires a telescope to observe. These pulsations occur because red giants are somewhat unstable. The balance between gravity and pressure is less secure than on the main sequence. Layers of the star can become ionized or neutral depending on temperature, changing their opacity to radiation. This can set up oscillations, where the star periodically expands and contracts, changing its surface area and temperature and therefore its brightness. For stars significantly more massive than the Sun, the red giant phase unfolds differently. These stars have enough mass that when their cores contract after exhausting hydrogen, they reach the critical temperature for helium fusion, about 100 million degrees Celsius. When helium fusion ignites, the core stabilizes once more, halting its contraction. These massive stars then spend some time as stable helium-burning stars. They may not even expand as dramatically as lower-mass red giants, because the helium fusion provides stable support from within. But this phase is relatively brief. Helium fusion proceeds much faster than hydrogen fusion, typically lasting only a few percent as long as the main sequence phase. Betelgeuse, that magnificent red supergiant in Orion, has already passed through multiple fusion stages. Its core has fused helium into carbon and oxygen, and has continued on to fuse carbon, neon, and oxygen into even heavier elements. The star has expanded to approximately 700 times the Sun's diameter, large enough to engulf Mars if placed at the center of our solar system. Its luminosity is about 100,000 times that of the Sun, making it visible across vast interstellar distances despite being roughly 650 light-years away. The surface temperature of Betelgeuse varies, but averages around 3,500 degrees Celsius, giving it that characteristic deep red color. The star is also somewhat irregular in its brightness variations. In late 2019 and early 2020, Betelgeuse dimmed significantly, dropping to about 40% of its normal brightness. This event generated speculation that the star might be about to explode as a supernova. However, further observations suggested the dimming was likely caused by a temporary dust cloud in the star's outer atmosphere, combined with natural pulsation cycles. Red giants and supergiants lose mass through powerful stellar winds. These winds are driven by radiation pressure, the outward push of the star's intense light on its outer layers. For a red giant like our Sun will become, the mass loss rate might be about 1/10,000,000th of a solar mass per year. This sounds tiny, but over millions of years, it amounts to a significant fraction of the star's total mass. More massive red supergiants lose mass even more rapidly. Betelgeuse is estimated to lose about 1 solar mass every 10,000 years or so, a tremendous rate that has likely shed several solar masses over its lifetime. This lost material doesn't simply disappear. It flows outward into space, enriching the interstellar medium with heavy elements forged in the star's core and brought to the surface by convection. The Hubble Space Telescope has actually imaged Betelgeuse's surface, one of only a few stars other than our Sun whose disk can be resolved. These observations reveal a mottled surface with bright spots and darker regions, likely the tops of enormous convection cells larger than the entire Sun. They also show the extended atmosphere and surrounding material ejected by the star's winds. As red giants age, they may progress through multiple episodes of expansion and contraction as different fusion shells ignite and extinguish. The details depend on the star's mass, but the overall trend is toward increasing instability. The star's outer layers become more loosely bound, more easily lost to stellar winds. The core continues to evolve, growing denser and in massive stars, progressing through increasingly rapid fusion cycles. Throughout the Milky Way, we can observe red giants and supergiants at various stages of this evolution. The Hyades cluster, about 150 light-years away in Taurus, contains several red giants among its 400 or so member stars. These giants form from the same molecular cloud as the cluster's main sequence stars, but, being more massive, evolve faster and have already left the main sequence behind. In the red giant phase, stars exist in a state of gentle crisis. No longer the stable main sequence stars they once were. not yet arrived at their final fate, they navigate a complex and sometimes unstable transition. They swell to enormous sizes, shine with great luminosity, and slowly shed their outer layers back into the cosmos. In their cores, the future is being prepared, the next chapter of their evolution waiting to unfold. Deep within the core of a red giant like our Sun will become, pressure and temperature continue to build. The inert helium core, supported by electron degeneracy pressure, continues to contract under the weight of the growing helium shell and the star's outer layers. The temperature climbs 80 million degrees, 90 million, approaching the critical threshold of 100 million degrees Celsius needed to fuse helium. In a star with less than about 2 solar masses, something dramatic happens when helium fusion finally ignites: the helium flash. This is one of the most powerful events in stellar evolution, yet it occurs completely hidden from view, deep within the star's core, invisible to any external observer. The helium flash occurs because the core is degenerate, supported by quantum mechanical electron degeneracy pressure rather than thermal pressure. In normal matter, when fusion ignites and temperature rises, the gas expands, which reduces density and temperature, providing a natural thermostat. But in degenerate matter, temperature increases don't cause expansion. When helium fusion ignites, the temperature skyrockets, accelerating the fusion rate exponentially, but the core doesn't expand to regulate the process. For a few seconds, the energy production in the core reaches about 100 billion times the Sun's current luminosity, comparable to the entire luminosity of the Milky Way galaxy. If this energy could escape the star immediately, it would be visible as a tremendous explosion. But it doesn't escape. The energy is absorbed by the overlying layers of the star, which gradually heat up and expand. As the core heats up, it eventually becomes hot enough that thermal pressure overcomes electron degeneracy pressure. The core becomes normal, non-degenerate matter once again. It expands, reducing its density and temperature. The runaway fusion moderates, settling into a steady helium-burning phase. The entire flash event lasts only a few seconds to minutes, but its effects reshape the star's structure. After the helium flash, the star settles into a new, stable configuration. The core is now fusing helium into carbon and oxygen through the triple alpha process. The star actually shrinks slightly from its maximum red giant size and becomes somewhat bluer and less luminous. It has reached the horizontal branch, a region of the Hertzsprung-Russell diagram where helium-burning stars reside. The horizontal branch stars and globular clusters provide beautiful examples of this evolutionary stage. In the globular cluster M13, located about 25,000 light-years away in Hercules, the horizontal branch is clearly visible as a clump of stars distinct from both the main sequence and the red giant branch. These stars are peacefully fusing helium in their cores, a phase that will last about 100 million years before the helium is exhausted. The helium-burning phase produces carbon, 12, and oxygen, 16, as its primary products. The triple alpha process first combines 2 helium, 4 nuclei into an unstable beryllium-8 nucleus, which exists for only about 10 to the power of -16 seconds before decaying back to 2 helium nuclei. Occasionally, though, a third helium nucleus collides with the beryllium-8 before it decays, forming stable carbon, 12. Some of the carbon, 12, can capture another helium-4 nucleus, forming oxygen, 16. The relative amounts of carbon and oxygen produced depend on the exact temperature and density in the core, parameters that vary slightly from star to star. This matters for the star's later evolution and, ultimately, for the composition of the planetary nebula it will later eject. For more massive stars, those above about 2 solar masses, the helium flash doesn't occur. These stars have enough mass that their cores reach helium fusion temperatures before becoming degenerate. Helium fusion ignites gently, controlled by normal thermal pressure regulation. These stars expand into red giants during their hydrogen shell-burning phase, then contract slightly when core helium fusion begins, becoming stable again for a time. The star Arcturus likely experienced a helium flash some millions of years ago and is now steadily fusing helium in its core. Its orange color and relatively modest luminosity, compared to its size, are consistent with a horizontal branch star. Meanwhile, the hydrogen-burning shell above the helium-fusing core continues to add helium to the core's outer edge, gradually increasing the core's mass. In the most massive stars, those above about 8 solar masses, helium fusion proceeds rapidly. A star like Betelgeuse exhausts its core helium in just a few 100,000 years. When the helium is depleted, the carbon-oxygen core contracts, heats up, and if the star is massive enough, which Betelgeuse certainly is, carbon fusion ignites. This begins a cascade of fusion processes, each creating progressively heavier elements. Carbon fuses into neon and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Finally, silicon fuses into iron. Each successive stage proceeds faster than the last. Carbon fusion might last 1,000 years, neon fusion about a year, oxygen fusion about 6 months, and silicon fusion only a day or so. The reason for this acceleration is that each fusion stage releases less energy per nucleon than the previous stage. To support the star against gravity, fusion must proceed faster, consuming the fuel more quickly. It's like a car going uphill that must burn fuel faster to maintain the same speed as the hill grows steeper. Iron represents the end of the line for fusion energy production. Iron, 56, is the most tightly bound nucleus. It has the lowest mass per nucleon of any element. Fusing iron into heavier elements doesn't release energy. It requires energy input. When a massive star's core is converted to iron, fusion can no longer support it against gravity. The core is doomed to collapse, but that catastrophic event is a story for our chapter on supernovae. For stars like our Sun, the helium-burning phase is the last stage where fusion provides significant energy. When the core helium is exhausted, the star will have a carbon-oxygen core surrounded by a helium-burning shell, which in turn is surrounded by a hydrogen-burning shell. This complex structure is inherently unstable, leading to the thermal pulses and planetary nebula ejection we'll explore in the next chapter. The transition from hydrogen-burning red giant to helium-burning horizontal branch star, punctuated by the helium flash in lower-mass stars, represents a critical juncture in stellar evolution. For a brief time, the star regains stability, its core once again providing the fusion energy needed to support the overlying layers. But this reprieve is temporary. The helium fuel is consumed much faster than hydrogen was, and another crisis awaits. Across the cosmos, this cycle plays out in countless stars. In young open clusters like the Pleiades, no stars have yet reached this stage. They're all still on the main sequence or just beginning to evolve into red giants. In ancient globular clusters like M13 or M3, thousands of stars are currently in the helium-burning phase, their horizontal branches clearly visible in color magnitude diagrams. Each star, regardless of its mass or age, must navigate these transitions according to the inexorable laws of physics. Gravity pulls inward, fusion pushes outward, and in the balance between these forces, the star's structure and evolution are determined. The helium flash, dramatic though it is, occurs in complete silence in the vacuum of space, deep within the star, witnessed by no one yet fundamental to the star's journey through time. As a star like our Sun exhausts the helium in its core, it enters one of the most beautiful and visually stunning phases of stellar evolution. The carbon-oxygen core, now inert, contracts once more. Above it, a shell of helium begins fusing, and above that, a shell of hydrogen continues its fusion. This double shell-burning configuration is inherently unstable, leading to a series of thermal pulses that ultimately result in the ejection of the star's outer layers in a magnificent planetary nebula. These nebulae have nothing to do with planets. The name is a historical artifact from the 18th century, when astronomers using small telescopes thought these round, glowing objects resembled planets. In reality, they are expanding shells of gas illuminated by the ultraviolet radiation from the dying star at their center. One of the most famous planetary nebulae is the Ring Nebula, cataloged as Messier 57, located about 2,300 light-years away in the constellation Lyra. When viewed through a telescope, it appears as a smoky ring of light, roughly circular, surrounding a faint central star. The ring is actually a roughly cylindrical shell of gas viewed roughly end-on. We're looking down the barrel of the cylinder, seeing both its near and far edges. The Ring Nebula is expanding at about 20 to 30 kilometers per second. The material we see was ejected from the central star roughly 6,000 to 8,000 years ago. The nebula glows in different colors: red from hydrogen emission, green from doubly ionized oxygen, and blue from ionized helium. These emission lines, characteristic of ionized gases at specific temperatures, create the nebula's otherworldly beauty. The process that creates a planetary nebula begins with thermal pulses in the dying star. As the helium-burning shell adds material to the carbon-oxygen core, the shell periodically becomes unstable. Fusion rates increase dramatically, causing the shell to expand and cool, shutting down fusion. The shell then contracts, heats up, and reignites in a cycle that can repeat hundreds of times. Each thermal pulse dredges material from deep within the star to the surface. Carbon and oxygen from the core reach the star's atmosphere, changing its chemical composition and appearance. The star develops a strong stellar wind, driven by radiation pressure on dust grains that condense in the cool, carbon-rich outer atmosphere. This wind carries away the star's outer layers at rates of up to 10 to the power of -5 solar masses per year, fast enough to remove the entire envelope in just tens of thousands of years. The ejected material forms an expanding shell around the star. Initially, this shell is neutral and invisible, but as the star's core becomes more exposed, its surface temperature increases dramatically. Eventually, the remaining stellar core, now a white dwarf, which we'll explore in the next chapter, becomes hot enough, 30,000 to 100,000 degrees Celsius, to emit significant ultraviolet radiation. This ultraviolet radiation ionizes the ejected gas, causing it to fluoresce in those characteristic emission lines. The nebula lights up, becoming visible across interstellar distances. The fluorescent process is similar to that in a neon sign. Ultraviolet photons knock electrons off atoms in the gas, and when those electrons recombine with atoms, they emit visible light at specific wavelengths. The variety of planetary nebula shapes is remarkable. The Helix Nebula, NGC 7293, located about 700 light-years away in Aquarius, appears roughly circular and is large enough to cover about half the diameter of the full moon as seen from Earth. It shows intricate cometary knots, small dense regions being eroded by the nebula's expansion, and has a complex structure suggesting multiple episodes of mass loss. The Cat's Eye Nebula, NGC 6543, located about 3,300 light-years away in Draco, displays an incredibly complex structure with multiple concentric shells, jets, and symmetrical features. High-resolution images from the Hubble Space Telescope reveal details down to a few billion kilometers, scales comparable to the size of our solar system. The complexity suggests that the central star may be part of a binary system. with the companion star's gravity shaping the ejected material. Some planetary nebulae are distinctly bipolar, with two lobes extending in opposite directions from the central star. The Butterfly Nebula, NGC 6302, located about 3,400 light-years away in Scorpius, is a spectacular example. Its two wings span about 3 light-years and are rich in dust and complex organic molecules. The bipolar structure likely results from material being ejected more rapidly along the star's rotation axis than around its equator. The chemistry of planetary nebulae is fascinating. Spectroscopic observations reveal not just hydrogen and helium, but also carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, argon, and even heavier elements. These are the products of fusion and nuclear processing within the star, now returned to the interstellar medium to be incorporated into future generations of stars and planets. Some planetary nebulae contain surprisingly complex molecules. The Helix Nebula, for instance, contains polycyclic aromatic hydrocarbons, PAHs, organic molecules consisting of carbon and hydrogen arranged in rings. These same types of molecules are found in sooty smoke on Earth and may be precursors to even more complex organic chemistry in space. The central stars of planetary nebulae are among the hottest stars known. The central star of NGC 2440, located about 4,000 light-years away in Puppis, has a surface temperature estimated at around 200,000 degrees Celsius, making it one of the hottest known stars. At such temperatures, the star emits most of its energy in the extreme ultraviolet, invisible to optical telescopes but detectable by space-based ultraviolet observatories. These central stars are contracting toward their final state as white dwarfs. As they contract, their surface temperature increases even while their luminosity slowly decreases. They're radiating away their remaining thermal energy with no fusion to replenish it. The stars move from the upper left of the Hertzsprung-Russell diagram downward and leftward, tracing a path toward the white dwarf cooling track. Planetary nebulae are relatively short-lived by cosmic standards. After about 10,000 to 20,000 years, the nebula has expanded and thinned to the point where it becomes too diffuse to see. The gas, now enriched with heavy elements forged in the star, mixes with the interstellar medium. Eventually, this material may become part of a new molecular cloud, contributing to future star formation. The Dumbbell Nebula, M27, located about 1,200 light-years away in Vulpecula, is a relatively nearby planetary nebula visible in binoculars. It has expanded to about 2.5 light-years across and is estimated to be about 9,800 years old. Its expanding shell is already beginning to merge with the surrounding interstellar medium, gradually fading from view as seen from Earth. Not all stars create planetary nebulae. Stars much less massive than the Sun, red dwarfs, will eventually exhaust their hydrogen, but will do so over timescales longer than the current age of the universe. Their evolution hasn't had time to proceed beyond the main sequence. Stars much more massive than the Sun bypass the planetary nebula stage entirely, exploding as supernovae instead. But for stars roughly 0.8 to 8 times the Sun's mass, the vast majority of stars, the planetary nebula phase is their swan song. It's a final, beautiful display before they fade into obscurity as white dwarfs. For a few thousand years, they illuminate vast regions of space with their colorful gases, creating some of the most photogenic objects in the cosmos. Astronomers have cataloged thousands of planetary nebulae in our galaxy. Each one represents a star's death throes, the final exhalation of material that once resided deep within a stellar interior. The gases glow with the rainbow colors of ionization, creating structures of haunting beauty. Spheres, rings, butterflies, hourglasses, and forms of such complexity they defy simple description. As we observe these nebulae through telescopes, we're witnessing the final chapter of stellar evolution for stars like our own Sunday. In about 7 to 8 billion years, when the Sun has exhausted its helium and begun its thermal pulses, it too will eject a planetary nebula. The Earth, if it still exists, will be engulfed in this expanding shell of gas, the atoms of our world mixing with the stellar material in a final cosmic reunion. For now, these nebulae serve as both scientific laboratories and works of cosmic art. They teach us about stellar evolution, nucleosynthesis, and gas dynamics. They also inspire wonder and contemplation, reminding us of the transient beauty that emerges even in the deaths of stars. At the center of a planetary nebula, after the outer layers have been gently cast off into space, there remains the stellar core, a dense, hot sphere about the size of Earth, but containing roughly half the mass of the Sun. This is a white dwarf, the final evolutionary stage for stars that began their lives with less than about 8 solar masses. It is no longer fusing elements in its core. Instead, it is simply radiating away its stored thermal energy, cooling gradually over billions of years. White dwarfs are extraordinary objects. Sirius B, the white dwarf companion to Sirius, the brightest star in our night sky, provides an excellent example. Discovered in 1862 by telescope maker Alvin Graham Clark, Sirius B orbits Sirius A at an average distance similar to that between the Sun and Uranus. Despite containing about 98% of the Sun's mass, Sirius B has a radius only about 1.7 times that of Earth. This extreme density has remarkable consequences. A teaspoon of white dwarf material would weigh approximately 5 tons on Earth. The matter is so compressed that atoms cannot maintain their usual electron shells. Instead, electrons are stripped from atoms and packed together in a state called electron degeneracy. This is the same quantum mechanical pressure that briefly supported the core before the helium flash, but now it supports the entire star permanently. Electron degeneracy pressure has a curious property. It does not depend on temperature. Unlike normal gas pressure, which increases with temperature, degenerate electron pressure depends only on density. This means a white dwarf cannot generate heat to support itself against gravity. Once fusion has ceased and the thermal pressure gone, only degeneracy pressure prevents complete collapse. The Indian physicist Subramanian Chandrasekhar calculated in 1930 that there is a maximum mass for a white dwarf, approximately 1.4 solar masses, a limit now called the Chandrasekhar limit. Above this mass, even electron degeneracy pressure cannot prevent collapse. White dwarfs above this limit do not exist. They are unstable and must either lose mass or collapse into something denser, a neutron star, if matter permits. Most white dwarfs have masses between 0.5 and 0.7 solar masses, the typical remnant core mass for stars like the Sun. More massive stars create more massive white dwarfs, up to the Chandrasekhar limit. Stars that begin with more than about 8 solar masses don't form white dwarfs at all. They explode as supernovae, which we'll explore in the next chapter. The surface temperature of a newly formed white dwarf can exceed 100,000 degrees Celsius, making it one of the hottest objects in the universe. But without fusion to maintain this heat, the white dwarf immediately begins to cool. Over millions of years, its surface temperature drops to perhaps 30,000 degrees, then 10,000 degrees, eventually to temperatures comparable to our Sun. Sirius B has a current surface temperature of approximately 25,000 degrees Celsius, making it white hot and very bright for its size. However, because its surface area is so small, only about 1/100th that of the Sun, its total luminosity is only about 2.5% of the Sun's. It is visible only because it's relatively nearby, at just 8.6 light-years from Earth. White dwarfs cool very slowly. The carbon-oxygen interior, created by helium fusion in the star's earlier life, is an excellent insulator. Heat must diffuse from the interior to the surface before it can radiate away. This process takes billions of years. The oldest white dwarfs in our galaxy, formed when the Milky Way itself was young, have cooled to surface temperatures around 3,000 to 4,000 degrees Celsius and glow a dim red. As white dwarfs cool, they undergo some fascinating changes. When the interior temperature drops below about 10 million degrees, the carbon and oxygen atoms can no longer move freely. They begin to arrange themselves into a crystalline lattice. The white dwarf literally begins to crystallize, turning into a giant cosmic diamond or graphite, depending on the exact conditions. This prediction, made theoretically in the 1960s, was confirmed observationally in 2019 when astronomers analyzing data from the Gaia Space Telescope found evidence of a pileup of white dwarfs at specific cooling stages. This pileup is exactly what would be expected as white dwarfs release latent heat during crystallization, temporarily slowing their cooling, the same phenomenon that keeps water at 0 degrees Celsius as it freezes. The white dwarf BPM 37093, located about 50 light-years away in the constellation Centaurus, has probably crystallized. With a mass about 1.1 times the Sun's and a temperature of about 12,000 degrees Celsius, its interior should be cool enough for crystallization. Given its composition, it's essentially a diamond the size of Earth. Appropriately, astronomers have nicknamed it Lucy after the Beatles' song Lucy in the Sky with Diamonds. Some white dwarfs have unusual compositions. Most are made of carbon and oxygen, the products of helium fusion. But white dwarfs from less massive stars, which never ignited helium fusion, are made primarily of helium. More massive stars might create white dwarfs with significant neon, oxygen, and magnesium content. The exact composition depends on the star's mass and how far through the fusion sequence it progressed. Many white dwarfs are found in binary systems, orbiting another star. About half of all stars are in binary or multiple star systems, so it's not surprising that many white dwarfs have companions. The white dwarf Procyon b, companion to Procyon A in Canis Minor, is located about 11.5 light-years away. It contains about 0.6 solar masses in a sphere slightly smaller than Earth and has a surface temperature of about 7,740 degrees Celsius. When a white dwarf is part of a close binary system, interesting things can happen. If the companion is still an evolving star that expands into a red giant, material from the giant can flow toward the white dwarf. This transferred material, rich in hydrogen, accumulates on the white dwarf surface. Eventually, enough hydrogen accumulates that its base, compressed by the weight of overlying material and heated by the white dwarf's heat, reaches fusion temperatures. But unlike fusion in a normal star's core, this fusion is explosive. The entire accumulated layer ignites almost simultaneously in a runaway thermonuclear explosion, dramatically brightening the white dwarf in an event called a nova. Novae can increase a star's brightness by tens of thousands of times over just a few days. The nova ejects most of the accumulated hydrogen into space at speeds of thousands of kilometers per second. Importantly, the white dwarf itself survives the explosion intact. Over years or decades, it can accumulate more material from its companion, leading to another nova outburst. Some novae are known to be recurrent, erupting every few decades. If a white dwarf in a binary system accretes enough mass to exceed the Chandrasekhar limit, approximately 1.4 solar masses, the outcome is far more catastrophic. The white dwarf can no longer support itself with electron degeneracy pressure. The core collapses, but instead of forming a neutron star, the carbon and oxygen in the core ignite almost simultaneously in a runaway fusion reaction. The entire white dwarf explodes in what's called a Type Ia supernova. Type Ia supernovae are among the brightest explosions in the universe, briefly outshining entire galaxies. Because they always occur at approximately the same mass, the Chandrasekhar limit, they have remarkably consistent peak luminosities. This consistency makes them valuable as standard candles for measuring cosmic distances. In fact, observations of distant type Ia supernovae in the late 1990s provided the first strong evidence that the universe's expansion is accelerating, leading to the discovery of dark energy. The nearest known white dwarf to Earth is Sirius B, at 8.6 light-years. But many more white dwarfs exist in our cosmic neighborhood. Within 20 light-years of Earth, astronomers have identified dozens of white dwarfs, most too faint to see without telescopes. These stellar remnants, cooling quietly in space, outnumber the brighter main sequence stars we typically associate with our stellar neighborhood. Eventually, after trillions of years, timescales far longer than the current age of the universe, white dwarfs will cool to the temperature of the cosmic background radiation, about 2.7 Kelvin. They will become black dwarfs, completely dark and cold, radiating no detectable light. No black dwarfs exist yet. The universe simply hasn't existed long enough for even the oldest white dwarfs to cool completely. The oldest white dwarfs we can observe have ages approaching the age of the universe itself, about 13.8 billion years. They formed from stars that lived and died in the Milky Way's early history. By studying these ancient white dwarfs, astronomers can learn about the galaxy's early star formation and the ages of the oldest stellar populations. White dwarfs represent the final fate awaiting our own sun and the vast majority of stars in the cosmos. In about 7 to 8 billion years, after expanding into a red giant, fusing helium in its core and ejecting a planetary nebula, the sun will settle into its twilight as a white dwarf. It will cool slowly, eventually fading from view over timescales incomprehensibly long. These stellar embers, scattered throughout the galaxy, serve as monuments to stellar evolution. Each one was once a vibrant, fusion-powered star. Now they rest, cooling and crystallizing, the last light of their fusion fires fading across the eons. In their patient fade, they embody the universe's long arc from activity to quietude, from fusion to darkness, from stellar youth to cosmic old age.